just discussing some ways of producing Schrödinger cats. And we were just discussing optomechanics, that is, light interacting with mechanical motion, which could give rise to a Schrödinger cat state in principle, so I'll just draw the setup again. So we have an optical cavity, but one of the mirrors can actually vibrate, for example, because it's attached to some cantilever. And so if a laser shines into the cavity and light circulates inside the cavity, there will be a radiation pressure force proportional to the intensity, proportional to the energy of light stored inside the cavity. And so when we discussed measurement, we already discussed how this could be used to measure the motion of the mechanical oscillator via the phase shift of the light beam, for example. But now we are also discussing the fact that since the force depends on the energy stored inside the cavity, we can actually entangle the optical field and the mechanical motion. And the simplest version of that idea would be to imagine you have a coherent superposition of many different photon numbers. Each photon number gives rise to a different radiation pressure force. So after some while, you will end up in an entangled state where different photon numbers are associated with different motion of the cantilever. So now I wanted to talk a bit about decoherence in such a setup. For example, imagine you have created a state involving a superposition of 1 and 0 phonons. This is the most modest kind of cat we can think of. Of course, if you are more ambitious, you will involve more phonons. Okay? Now, how to calculate the decoherence rate in such a case? Well, if this is the harmonic oscillator potential for my mechanical motion, then these are the energy levels of the harmonic oscillator. If it's in its ground state, then there are 0 phonons. If it's in the first excited state, we say there is exactly 1 phonon, and so on. So now imagine we have placed it, for example, in a superposition of state number 0 and state number 1. Then obviously this superposition can be destroyed for the simple fact that because of the damping of the mechanical motion, the system can relax down to the ground state. Also, if the system is actually at some finite temperature T, so there are always these thermal vibrations in the substrate to which the cantilever is coupled, then once in a while a thermal phonon, a thermal vibration, will go into the cantilever and excite its motion. So in that case, we also have a rate that takes us up from the ground state to the first excited state, but nevertheless, since this is a thermal phonon which is completely incoherent, it will also destroy the superposition. So these are the bad processes. Now, what is the rate, for example, to go down from 1 to 0? Well, it turns out, of course, this rate is connected to the damping rate. And at 0 temperature, that would be everything. But if we are at finite temperature, then in addition to this spontaneous emission, given by the rate gamma, we also could have some thermally induced emission, because there's a finite number of thermal phonons. So this rate actually gets multiplied with n thermal plus 1, and n thermal is really the occupation of the environment at this particular frequency, the frequency of the cantilever mode, called omega, and also given by the temperature. So that would be given by the Bose-Einstein distribution. So this makes things worse at higher temperatures. And if you ask me, okay, what is the corresponding way to go up from 0 to 1? This is also given by gamma as a prefactor, but then we can only absorb thermal phonons. So that would only be given by n thermal, and if the environment were at 0 temperature, which usually it is not in these experiments, then this weight would completely vanish. And likewise, there are weights, for example, taking you further up. So, if I then want to have an estimate for my decoherence rate for such a situation where I'm in a superposition of maybe the first few excited states, then it's really given by this gamma times n thermal, maybe +1, but now I would imagine a situation where the temperature is much higher than the h bar omega, so that n thermal really overwhelms this extra factor of 1. So then I will allow myself to just define gamma phi as gamma times n thermal. And in any given situation that you want to describe, you better solve the master equation to really find out for your particular state what is the effective rate at which it decays. But this sets the scale. Now, let me just rewrite this so we see how this is connected to the properties of this mechanical object. We already see, of course, it would be better to have a mechanical object with a very small damping rate. Also, it would be better to have a low temperature because then this is small. But I want to write this down in a different combination. And so, first of all, this and thermal, if the temperature is high enough, I can just very simply estimate because I can say the total energy stored inside a harmonic oscillator at temperature T is just kBT. And I divide it just by h bar omega, which is the energy quantum, to find the number of quanta. So that would be gamma kBT divided by h bar omega. And now there is a definition, namely this ratio of omega over gamma, which appears here. This is what people call the quality factor of the mechanical oscillations. And it's somehow the number of oscillations you do before your energy is decayed to 1 over E. So the picture you should have in mind, even in the classical case, is you have these decaying oscillations due to the finite damping rate, and then there are Q oscillations. Okay. Now, that means for our purposes, if I insert that, then the dephasing rate is set by kBT, which is the thermal energy, divided by h bar Q. And so, obviously, well, I want to reduce the temperature, that is clear, but there are limits to that, and usually it's about 20 millikelvin you can go down to, and even that is quite hard to achieve if you really want to have a setup where you simultaneously send light into the setup. But then on the other hand, as far as your setup is concerned, you want to make Q very large. And so, what determines Q? Well, that is different from setup to setup. What are the most important contributions to limit the value of Q? But for example, in some setups there are tiny defects inside the vibrating object, and the vibrations can dump their energy into these little defects and excite them. But even if your material is perfect, if you have a perfect crystal, then still, if you look at this picture, you see that this cantilever is connected to some support because it doesn't float in free space. And so any vibration can then easily radiate away sound waves into the support, and likewise thermal vibrations can go into the mechanical vibration, and this mechanism is simply called as clamping losses. So this mechanical object is clamped here, and you're losing energy at this point. So essentially you emit sound waves into the substrate. And you can already guess that this, in particular, this can be controlled very much by the geometry. One typically example of how to control it would be you have different mechanical normal modes of vibration of your structure, and you would want to choose it such that the point where you are connected to your substrate is really a node of the vibration, where the vibration amplitude is 0, because then you don't transfer anything. Or maybe you are connected at several points, but there is some destructive interference going on. Okay, so what are the typical cues? Well, the cue can be, well, it can be very bad, but what are the typical good cues? That would be, well, up to 10 to the 7 for good setups. That depends on the material. 10 to the 7 would be, for example, a silicon nitride membrane. Now, if we look at this, and we want to improve Q further, one simple idea, a very powerful idea that people have come up with is somehow to get rid of the support, to make sure that the mechanical object is somehow really floating in free space. So, well, there are many different ways of levitating some object, for example with magnetic fields or so, but what we have in mind here, since we're talking about interaction with light anyway, is to create a standing wave of light. And then to trap some dielectric particle in there. So, for example, you can think of a small glass sphere. And the typical dimensions might be, say, on the order of 100 nanometer or something like that. So there are advantages and disadvantages, and people are still trying to choose the perfect size, so to speak. Now, because this is simply trapped in free space and is not materially connected to anything, you simply don't have any clamping losses. And all that remains is, for example, that there are still some gas molecules here which can hit this glass sphere. Also, if you think of what we have said about the molecules, this could be hot and emit some thermal radiation, possibly. So all of these factors have been estimated. And in principle, you should be able to get very good coherence times, and there are several teams now working on implementing this. Let me just mention one nice idea in this context of how to create sort of microscopic superpositions. Because you see, one of the problems, even if you were to create a superposition of the particle being here or there with a displacement, say, given by a few times the 0-point displacement, that is the size of the ground state, in comparison to the total size of the object, this is still very tiny. So if you remember, a typical estimate for the size of the 0-point fluctuations was femtometer, but if the size of the object is 100 nanometer, then you almost don't notice it. And so, how can you change this? One of the ideas, and now I'm recounting the story of Oriol Romero-Izard and Ignacio Celac, is first you trap it there, but then at some point you simply switch off the lattice. And if you have switched off the lattice, what had been formerly a localized wave packet will now expand freely, that is ballistically. Now, of course, this in principle is already a coherent extended state, that is nice, but in order to prove the coherence, you want to do some interference experiment to prove that this part of the wave function is really still coherent with that part of the wave function. But in order to do a coherent interference experiment, you need something like a double slit or a grating or anything. This is not yet good enough. And so there was a very smart idea. Since all of this will be sitting inside a cavity anyway, you can again try to do a measurement of the phase shift of some reflected light beam. And it turns out that, of course, this phase shift is proportional to the pull of the cavity frequency. If it pulls more strongly, the phase shift will be larger. But this pull of the cavity frequency by the presence of this glass sphere depends on the position of the glass sphere. And how does it depend on the position? Well, that is pretty easy. If you calculate it, it depends on the intensity of the standing light wave at the position of the particle. If the particle is sitting in a node, it has no effect whatsoever on the light field. So this frequency shift depends on the intensity at the position of the particle. So if sine kx would be my amplitude of the standing light wave, and sine squared kx is the intensity pattern. And now you see that, well, this may be the intensity pattern. You see, if I measure this, and I'm looking at a situation where my particle is really sitting in a minimum or maximum of this sine squared function, then there is an ambiguity in the signal. Because if I'm sitting here or I'm sitting there, I will get exactly the same phase shift. That's simply a property of the sine squared. And so, if I have really precisely measured my phase shift, I have, so to speak, collapsed the wave function onto all the positions which are compatible with this value of theta, but there is more than one position. In particular, there are these two positions. So suddenly, depending on detecting a certain phase, something like this is created. You cut out of your initial wave function these two delta peaks because these are compatible with this phase shift signal. And then, of course, that's great because that's how a wave function would appear behind a double slit. So now you can just let it expand freely, and after some time, well, one part of it will expand further to the left and nothing particular happens there. But another part will expand to the right and interfere with another wave, and then you should see an interference pattern like this. And that, in principle, now you can try to measure and convince yourself that actually there is an interference pattern. If there was no coherence left between these two places, then you wouldn't see an interference pattern. So this is the kind of experiment that people are planning on doing. And so you see that here the light field has been used for several purposes. It has been used to trap the particle and manipulate the trapping potential, but it's also being used to do this measurement, which prepares the double slit situation. Okay. So I don't even want to say more about this field. There would be so much to say, but let me just then switch to yet a third way of producing macroscopic superpositions. And this is even the first approach that people have been taking, how all of this endeavor came about. That was started in the 80s, in particular the name of Tony Leggett is connected with it, and that is trying to produce macroscopic superposition states in superconducting circuits, that is, metals having been cooled down to very low temperatures, such that currents flow without resistance, and you can try to create coherent quantum superpositions. Now, let me explain the typical situation, or one of the first experiments in which this was analyzed. If I have any piece of superconducting matter like this sphere, and I switch on an external magnetic field, then what will happen is that currents are induced in this metallic sphere, like it would also happen for the normal conducting case. These currents have the tendency to expel the magnetic field. Only in contrast to the normal conducting case, the currents run forever, so the magnetic field remains expelled. And so the situation is like this. Okay, so this is the first situation you should have in mind. Now, things get even more interesting if instead of just having a sphere, you have something like a torus or a ring. It turns out that also this has the tendency of excluding the magnetic flux. Sometimes, depending on how you arrange things, maybe you already have the magnetic field before cooling down, it might happen that some magnetic flux lines get trapped inside the ring. But it turns out that the system wants to have exactly an integer number of so-called magnetic flux quanta inside the ring. So this is called flux quantization. So the magnetic flux inside the ring, that is magnetic field times area, is some integer multiple of phi naught, and phi naught is called the superconducting flux quantum, h over 2 times the electron charge, and the value would be about 10 to the minus 15 Teslas per meter. Okay. Now this is also some fact about superconductivity. But now imagine your ring is quite thin, or maybe it has some weak link somewhere. In all of these cases, the current that can be produced by the ring is not so strong anymore. It cannot really see to it that the magnetic flux is exactly an integer multiple of the flux quantum. Yeah? So that is the interesting situation we now want to consider. And you will see why this is interesting, because in the end you can have superpositions of different values of the flux. So let's draw this. Okay, so here there's supposed to be a tunnel junction or a weak link or anything that somehow breaks the ring, and that means your current cannot be too large. But still, there is still this tendency that the ring would like to have a magnetic flux that is as close as possible to an integer multiple of the flux quantum. Okay? So there is still some tendency left for currents to flow. And now it turns out that you can be very cruel to the ring and set the nominal magnetic flux, so to speak, the externally applied magnetic flux, that would be there in the absence of any currents flowing, just to half a flux quantum. Because then the ring cannot decide whether it likes more to be at 0 magnetic flux or exactly 1 magnetic flux. Yeah? And then these two possible states are simply equal in energy. And what will happen, because of other terms in the Hamiltonian connected to the charging energy, is actually that you will get a superposition of these two possibilities. Now here in this picture I will only draw the current running around in one direction, but in reality you can engineer a superposition. So you arrange, so to speak, the two states where the current runs counterclockwise and clockwise. You arrange them to have the same energy. And again, you arrange this by just setting the external magnetic field and thereby this external flux to be just half a flux quantum. And then the system actually chooses as its ground state a superposition. So I didn't want to go through the details of writing down the Hamiltonian, but this really follows from describing these superconducting circuits in a quantum mechanical fashion. And the idea then is, here we have our two components of a ket, at least provided the current is in some sense of a macroscopic size. And so there have been a number of attempts, but probably the first group that really succeeded in this was the Lukens group in 2000. And so they claim they really have a superposition of macroscopically different states. So what are their numbers? What are their claims? For example, if you take the difference in current between these two states, I mean, one flowing this way, the other flowing that way, it is on the order of 2 microampere. That already counts for a sort of macroscopic current. If you take the difference in magnetic flux, it's on the order of a quarter flux quantum. Well, then you can say, okay, maybe this should count only as microscopic, I don't know. And if you, however, take the difference of magnetic moment, which is current times area, then you find this is about 10 to the 10 Bohr magnetons, where Bohr magnetons is, so to speak, the microscopic unit of magnetic moment. And the Bohr magneton, just to remind you, is the electron charge times h bar over 2 me. It's the magnetic moment of a single spin, and it would be 10 to the minus 23 ampere meter squared. So, at least for them, they would claim they have a superposition of macroscopically distinct states in the superconducting circuit. And now, of course, also if you look at more recent experiments where people use these kinds of devices to produce qubits, because they have a two-level system, they could also, at least with the same right, sometimes claim that we are having a macroscopic superposition. Now, still you might not be convinced, because it seems to depend on what you look at. And so there has been this question of, how do I measure the size of a ket? Sometimes it seems to be clear, or at least partially clear. For example, if you look at these molecules in the interferometer of the Arndt group, then it makes some sense just to count the number of atoms. And if you have 200 atoms instead of 100 atoms, then somehow your ket seems to be twice as large. On the other hand, if we think, for example, of these optomechanical experiments, to give a simple example, then if we have a superposition of the sphere being in this position or in that position, which is just slightly displaced, then it would not be quite fair, I believe, to say, let's just count the total number of atoms and then this is somehow the size of the ket. Possibly you should rather count only those small fringes where the two configurations differ and then count the number of atoms inside these fringes, for example. The situation is even more severe in such a case because you could say, oh, this contains billions and billions of electrons and somehow they are going clockwise or counterclockwise. This is the size of my ket, the total number of electrons, but that wouldn't be quite fair because if you know anything about electronic systems, usually they have this Fermi sea, which is completely filled, which is quite inert and doesn't change very much. And all these effects like superconductivity only happen near the Fermi surface, where then a few electrons are rearranged into Cooper pairs and then rearranged into yet another pattern to make the current flow. And so you should probably not count all the electrons as participating in this phenomenon. So it's a reasonable question, at least, to ask what is the size of such a ket. Now, one of the oldest approaches current or magnetic moment, and trying to refer them back to some microscopic unit. So at least for the magnetic moment, it is reasonable that you compare it against the Bohr magnet. So you just take the difference in some observable and you compare against some microscopic units. This is not terribly well defined because you can pick your observable and you can pick your microscopic unit. Also, for example, in the, say, interferometer experiments, you could ask yourself, well, should I also factor in the distance between the two positions that occur in the superposition? And what should I compare it against? Should I compare it against the size of the molecule or what? So that's not entirely clear. Now, of course, this is not very mathematical. You just take your numbers and choose some comparison. Another rather early attempt to be a bit more quantitative is due to Leggett, and he introduced something that is called the disconnectivity. So, the idea is you're looking at a large system composed of some total number of particles, and you're given some quantum state of this total many-body system. And you're not quite sure, is it a very simple product state, for example, where all the particles are independent, and certainly then you wouldn't call it a cat? Or is it rather really a macroscopic superposition where, say, all the spins are down or all the spins are up and you have a superposition of these two different versions? Now, how to distinguish between that? Well, the qualitative idea is things are more macroscopically quantum mechanical if there is a lot of entanglement. And that means also there are lots of quantum correlations between different parts of your system. And so, in order to quantify this, the idea then was to pick a part of the system, say with n particles, and then do what? Well, we have already learned the idea when we discussed entanglement, although this predates all these entanglement measures. Namely, the idea is if this part of the total system itself is in a pure state, then it was in a product state with the rest of the system. So then there was no entanglement between this part of the system and the rest. But how do you check whether this part of the system is in a pure state? Well, you look at its reduced density matrix, and then there are several possibilities, but one of the possibilities is just to calculate the entropy. The entropy is 0, it's just a pure state, it's just a single state. So the idea is to calculate reduced density matrices, like rho n is the trace over the rest of the system of the total density matrix. And then to calculate the entropy connected to this rho n, let's call it Sn, minus trace rho n log rho n. You see that here, following Leggett, again I take the natural logarithm instead of the space 2 logarithm, but I leave out the kb to get some dimensionless number. And then the basic idea is to see how this entropy behaves as a function of the subsystem status. So it's best to draw some examples. Now, the general idea is if the total system is in a pure state, then at some point probably the entropy should go down to 0. On the other hand, if I pick a small subsystem, then probably it's entangled with a lot of the rest of the system. So then I could imagine that I have a rather large entropy, and at some point this decreases. And the idea would be if this decreases already at relatively small subsystem numbers, then probably I don't have a very large cat. There are only short-range correlations. If it decreases at a rather large subsystem size n, then probably I have a large cat. And it's something like the Greenberger-Horn-Zeilinger state, for example, if this were a spin system. Now the only problem with that is something which we already learned about in entangled states. It's very easy to quantify the entanglement of pure states. It's much harder to quantify it for mixed states. And so, for example, if the total system is in a mixed state, then of course even the entropy for the total system is still relatively large. So then the situation could look like this. So that would be a mixed state, and that would be cat, and somehow this is the size of the cat. And so what Leggett did then is to introduce a measure which gets rid of these mixed state situations and only sort of keeps these true cat situations, somehow by comparing the entropy to all the entropies for smaller sizes n. And so just to check whether the entropy is flat like this or whether it nicely goes down at some point. Okay. But there are more measures for the size of your cat. So I already mentioned this Greenberger-Horn-Zeilinger state, which is a very nice example of a cat. Up, 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 plus down, 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 down is probably a cat of size 4, as far as I'm concerned. So just to remind you, the GHZ state would be, for example, up, 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 plus down, 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 down. And everyone would agree that somehow there are 4 spins, and this is a cat of size 4. But now what happens if you take a generalized GHZ state to make it more interesting? And by generalization, I just mean that instead of taking just down, 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 I take another single spin state, which is almost parallel to the initial state. So just the GHZ prime could be a superposition of up, 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 plus something which is almost up. And that you could quantify by the overlap, for example. Let's say up, overlap with this one is almost 1. So let's say the squared is 1 minus epsilon squared. And as epsilon tends to 0, these are simply the same states, and then you wouldn't call this a cat. So somehow the effective size of the cat must have to do with this epsilon. And so how to quantify this? Well, in 2002, Dürr et al. Considered precisely the cat size for this class of states. And they even had 2 different versions of quantifying the cat size. One of them was related to the decoherence. Yeah? You know, and we discussed this already a little bit, if this is subject to some external field, yeah, then since each of the spins acquires a phase, the total phase acquired would be 4 times the individual phase, for example. So these phases add up. So in particular, if there are some fluctuations, some external fluctuations leading to decoherence, then the relative phase between these 2 states will decohere faster than the relative phase between a simple single spin, up plus down. And so what they did is to set up a simple model of decoherence for these superpositions and to quantify the decoherence rate and extract from this decoherence rate an effective size of the superposition. And so for them, then their cat size was somehow n times epsilon squared, which makes sense. If epsilon goes to 0, these states are the same, the cat size goes to 0. So that was, first of all, taken from this effective decoherence rate. But then in addition, they also said, well, this is a very nice entangled state, a highly entangled state. This is probably not a very well entangled state. So how much entanglement can we distill out of this state? And that you can also take as a measure of the cat size. And it turns out, properly defined, it gives rise to exactly the same expression for the cat size. So that is nice. The downside is, of course, that this was only done for this class of states, for the generalized GHZ states. And so you would want to be able to apply these things to real states that occur in experiments, like the state of a squid, the state of a superconducting circuit or something like this. So other proposals have been made. There is a proposal which says, well, let's try measurements. Let's try to ask the question, how easily can I distinguish the two states involved in the superposition? Because if you look at the GHZ state, and you are allowed to measure even only one single spin, this is already enough to decide whether you are in this branch of the superposition or the other branch. Because if you measure the first spin and it's up, then you know, aha, I'm in this state. Everything collapses to this state. If it's down, then you're in the other state. But if you do the same kind of measurement to decide in which branch you are in, applied to such a generalized GHZ state, you see if I measure up, well, possibly I'm here, possibly I'm there. The likelihood is a little bit larger here, but I can't distinguish it very readily. And so I would have to measure more and more spins to finally be sure, it's probably this branch. So that is an idea you can try to generalize. And that has been done. So still you imagine that you have somehow n units, like these n spins, and then you ask, how many measurements do I have to make? So how many subunits, how many units do I have to measure in order to be able to distinguish with a given precision between the two branches? And so let's call this little n, and then you would say, well, if I need many measurements, then it's more likely a situation like this. If I need only a single measurement, it's probably something like the GHZ state. So then the cat size, they define as taking the total number of units divided by this number which you have to measure. And so that gives reasonable estimates, and this you can read in Korsbakken et al. In 2007. Okay. So we also at some point looked into this. Our idea was the following. Going back to the cartoon I've drawn, if you have a big massive particle in such a superposition, you could ask, well, how many atoms do I really have to move in order to go from this configuration to the other configuration? Or if you are looking into electronic systems, you could imagine a situation like this. If that is the band structure of an electronic system, energy versus K, then usually you will have a filled Fermi sea. But then maybe you have created a situation where several electrons are going to the right, introducing a current that is flowing to the right. and now you want to superimpose it with another state where you exactly have the same situation, only the electrons are going to the left, current flowing in the other direction. So again, there's this Fermi sea, but the surplus electrons, so to speak, are now traveling in the other direction. And so our idea was to ask, well, how many electrons do I have to move around, so to speak, to go from this state to the other state? And that you can make more formal. You can say the operations I allow myself are single particle operations. So a single particle operation in second quantized language, you would say, I take my electron out of state L and I place it into state J. This is an example of it, only with L and J referring to momentum states. And then I can count the average number of these single particle operations that I have to perform. And if you want to read about it, this is Abel et al. 2008. With all these measures, they have been applied to some examples, and typically they work better for some examples than for other examples. But the mathematical structure can get quite involved, and often the calculation and effort can also be quite large. So I think this is a general feature if you don't restrict yourself to a very specific class of states. Okay. So now I wanted to close that chapter on decoherence and the Schrödinger cat, unless there are some questions remaining. And if there are no questions, I wanted to go to the next chapter, which is to deal with interpretations of quantum mechanics. And with interpretations, I mean you take the structure of quantum mechanics as we know it, and you just tell the story differently. But as we will see, there are stories which you wouldn't recognize at first glance. Still, the requirement for this chapter is that the predictions are the same as standard quantum mechanics. And then in a later chapter, we will even discuss extensions, where people play around with the theory, and in principle, there would be experiments that distinguish the different approaches. But for now, let's just stay with interpretations. So the predictions are the ones we know, but you can tell the story in different ways. Okay, so of course the standard against which to compare is always this textbook Copenhagen interpretation, and so I will be very brief here. This is what we've been doing all the time. And of course, with all these interpretations, at least once they get philosophical, it's a little bit dangerous because I might be misrepresenting the people who originally put them forth, but I just take a very practical-minded approach, so I just write down what I think is the Copenhagen interpretation. Now, I think there are two main ingredients of the Copenhagen interpretation of quantum mechanics. The first is to say that, so to speak, under usual circumstances, a quantum system just evolves according to the Schrödinger equation. So you have this unitary quantum evolution. This works for a single particle, works for many particles, works for quantum field theories, works in the relativistic case. But at this point, you're not supposed to ask what the psi means. Now then there comes a second step, which is completely disjoint from the quantum evolution, which is the measurement. And so the measurement is separate. And the story goes that this is when your quantum system, for example your particle, interacts with some macroscopic classical measurement apparatus that can give you a definite measurement result. And so then you would use the wave function to predict probabilities with which certain outcomes would appear. So for example, if it were an x measurement, you would have psi of x squared. And then if this outcome does appear, the wave function has to be collapsed onto this state, for example, onto a state localized at a specific point x. And then somehow the value x or p or whatever you measure has become real, but only at this point. And it's strictly forbidden to imagine that somehow, even before the measurement, there were some values, only you wanted to discover those. Before the measurement, nothing was real. So in particular, this means there are no trajectories, because that would mean that you have the position at all times, even if you don't look at the particle, even if you don't measure, and you're forbidden to even think in this direction. Also, if you try to analyze the measurement process, you'll find, yes, if I do measure the position, I will scramble the momentum, and so in subsequent time steps, the evolution will be completely different from what the evolution would have been if I hadn't measured my particle. So that is another indication that you are not allowed to think of the trajectory. Okay, so that's my brief summary of the Copenhagen interpretation. And you know, for example, when we discussed the EPR experiment, that Bohr insisted this prescription should be adhered to, even if the two parts of your system are very far separate, even if it sounds a little bit spooky, like spooky action at a distance, if you adopt this, but the whole measurement configuration, even if it consists of measurement plan settings at very separate places, should be taken into account to work out what is the result. And only then the values become real. Okay. Now, you see that trajectories are forbidden, and so the first interpretation, the first non-standard interpretation that I want to discuss here in this chapter is then the so-called Bohm's hidden variable theory, which precisely introduces trajectories into quantum mechanics and does it in a way which is completely consistent with standard predictions. So the setup is that you ask the question, are we allowed to think of a trajectory? The usual answer would be no. First, on principle grounds, because Bohr has said so. Also, second, because you analyze the measurement process, and indeed you find if you want to measure very precisely the positions, then in the end, if you increase your precision, you will just end up with a random walk that you observe instead of the real trajectory of a ballistic particle. So it seems that the answer is no. Nevertheless, it works. And so this is mostly due to Bohm in 1952. But actually it turns out that already de Broglie had this idea in 1927. It had even presented it at a Solvay conference. There had been some opposition back then, and so he had dropped the idea. So Bohm was the one to really work it out. Now, what is the basic idea? The basic idea is we still need the Schrödinger equation. We still need the wave function, but we still want to have a definite position of our given particle at any moment in time. And so we want to have a trajectory. And the idea is somehow, and we will specify how this works, that the wave function acts like a pilot wave, a guiding wave that tells the particle how to move. Think of a water wave and some small object swimming on the water, and it would certainly be influenced by the surface water wave. Now, how does it work? So first of all, the particle at all times is described both by knowing the wave function but also by the position of the particle. The wave function is in the background, its purpose is to guide the particle. Now, what is the equation that this trajectory should fulfill? Well, here is the equation. So the time derivative, it's the first time derivative of the position, is given by some velocity field that has some value at this position and at this point in time. And the velocity field is derived from the wave function. Namely, if you tell me the phase of the wave function, I tell you the velocity field. So it happens to be h bar over m times the gradient of the phase evaluated at this position. And so the phase is simply taken from the wave function. So psi at any point you would write as the modulus of psi times e to the I phi. So that is the important guiding equation of Bohm's theory. There is another ingredient, namely, you still imagine it's a statistical theory. So yes, in one of the experiments, your particle is there and moves according to this equation as the wave function evolves. In another one of the experiments, you started at a different point. And so in your mind, you think of an ensemble of trajectories, even though in every single one is supposed to be really a definite trajectory. This is very similar to classical statistical physics, so this is nothing mysterious. But you can ask, okay, so if I want to describe an experiment, what should the random initial conditions look like? How should I distribute my ensemble of particles initially? And the answer is, you should distribute it according to psi squared, at least initially, at the initial point. So t equals 0. R of 0 should be distributed according to psi squared. So you have your distribution of initial points in time, you evolve your wave function according to the usual Schrödinger equation, and then you evolve your trajectory, any given particular trajectory you evolve according to this guiding equation. And the beauty of the setup is that if at the initial time your positions were distributed according to psi squared, this guiding equation will make sure that even at all times the probability density of your ensemble coincides exactly with psi squared. And so this is remarkable that we want to show now. This is why you have to choose this guiding equation and not any other. Okay, but before we check that this is the case and this always works out, let us just look at a very simple example, namely if I just have a plane wave or a very extended wave packet that basically looks like a plane wave. So the idea is, say this is my wave packet where psi squared is large. And now I'm drawing, since the phase is important, I'm drawing the lines of constant phase. So let's say these are the lines of constant phase. So to speak, the wave fronts of my wave packet. And now since the velocity is oriented along the gradient of the phase, it will be perpendicular to these lines of constant phase. So my particle will just move in this direction. So that would be the velocity v. Now, that seems good because we know that if I have a plane wave, then this is also the direction of the momentum. The only thing we have to check is whether even quantitatively the speed matches what I would expect. And so that's easy to say. For example, for a plane wave, my phase is just k times r, e to the high kr. And so the velocity, according to Bohm's theory, is h bar gradient phi over m, which is gradient phi is k, is h bar k over m, which is just the momentum of my plane wave divided by m. So this is the velocity that I would expect. So at least in this case, it does make some sense. Now let's see, just to prove that indeed, if the distribution matches at the initial time, it will match at all times. So I will say that rho from now on is the probability density according to Bohm's theory, which in the end will be the same as psi squared. But for the moment, rho is the one for Bohm's theory, and we want to check whether it's equal to psi squared. So rho of RT is the probability density for my Bohmian ensemble, so to speak. Always keeping in mind that in any given experiment, it's not a swarm, it's not an ensemble of particles that is moving. Yeah? This is only conceptually averaged over many experimental runs, like in classical statistical physics. So the claim is, if rho and psi squared match at time 0, they match at all times. Okay, so how do we check that? Well, I will just calculate the time derivative of rho at a particular point in time and then transform it and check to see if it's the same as the time derivative of psi squared, provided that up to this point in time that has been true, and then it will be true for all times. Okay, so time derivative of rho. Well, we certainly have a continuity equation. We have this ensemble of particles. none of the particles vanishes. I have a velocity field for these particles. So the time derivative of rho is simply minus the divergence of the corresponding current density. Let's call it J bohm. And J bohm is then simply rho, the density according to Bohm, times V, the velocity field according to Bohm. So, well, this is rho times h bar over m gradient phi, of course, according to the guiding equation. And now I assume that up to the point in time that I'm considering, my assumption here has already been true, and rho and psi squared coincide. So I can replace rho by psi squared. And then I have something which is only dependent on the phase and the modulus of the wave function. And you can work out that this is actually the same as the real part of psi star minus I h bar gradient over m times psi. This is the expression which I think we discussed in the beginning for the quantum mechanical probability density current. And you realize, okay, this is the momentum operator divided by the mass, so it's something like the velocity operator. On the other hand, if you apply it to psi, the gradient can act on two components of psi. It can act on the magnitude of psi or onto the e to the I phi part. If it acts onto the magnitude of psi, it turns out that the resulting expression will be completely imaginary, and that part will then vanish when I take the real part. On the other hand, if I act the gradient on the exponent, I will get I grad phi in here, and I will get precisely the one up here. So that's the same, and that is the quantum mechanical probability current density. And so, since they are the same, and the time derivative of rho is minus divergence J bohm, time derivative of psi squared is minus divergence J quantum mechanics, they are the same. So, what this means in particular, if I insist on this initial condition, that initially at least my ensemble is distributed according to quantum mechanics, and then I have the guiding equation, then the distribution will be perfectly correct at all times. In particular, when my particles finally hit a screen to reveal an interference pattern, their probability distribution will be perfectly correct. And so, assuming that all my measurements in the end are really only measurements of position, I'm fine. There will never be a contradiction with the standard predictions of quantum mechanics. And I will argue later, and we already essentially argued when we discussed measurements, that even if you do a, say, momentum measurement, in the end, really, you do a position measurement. And you just have a specific measurement setup, and that, of course, you would have to simulate in here. Now, maybe an example will help to see what's going on. And so the first example here, besides the plane wave, of course, will just be the double slit. So how does it look like for the double slit? Well, so here's my double slit. And so now what you should do, and here's the screen, say, what you should do is to calculate the wave coming in as a plane wave from the left and then being transmitted through these two slits and giving rise to the interference pattern. And say you calculate a steady state, a stationary state for your wave, scattering state. So as these waves, these wavefronts interfere, there will be areas that are dark and areas that are bright because of the interference pattern that emerges. And now, there's a non-trivial phase configuration in here. And if you really work out how the trajectories behave, it's something like this. They have patterns like that. So that could be one trajectory. And it would hit the screen here, for example. And if you calculate the next trajectory, it might look like this. Now, it turns out these trajectories never cross because if I'm in a stationary situation, the gradient field, the velocity field is just unique. It's, if you're at some point, there's just a unique velocity associated with it. You can never have two crossing trajectories because that would mean you have two different versions of the velocity field at this point. So they never cross here. And now, how does the pattern emerge? Well, there are some landing up there, then there are fewer trajectories in some region. There are again more in between, and maybe even more, depending on the wave configuration. Even more in the middle of the screen. And you can continue this, but what you then see is that a pattern emerges, and this pattern is simply the interference pattern that you expect from quantum mechanics. Maybe it's not completely nice, but it should be symmetric around this axis. You can see how it works out. Yeah? First you calculate the wave equation, you get the phase field, and you calculate the particle trajectories, and you find that they somehow cluster at the places on the screen where you expect them to go. So that was the double slit. And so that's pretty nice. This is also the generic behavior for these interference effects in Brooks theory. The next question is what happens, for example, in the ground state of the hydrogen atom? Well, we have a particle going around in a classical orbit, Kepler ellipse, or what? So it turns out the hydrogen atom maybe is a little bit of a disappointment. So if that is, say, the psi squared, the density of the ground state, and this is the nucleus, and it turns out the electron just sits there. And the reason is simply, if you think about it, the ground state is just some stationary state. It has no phase gradient. Yeah? The phase just evolves in time, but it is not position dependent. Because gradient phi equals 0, and that would be true for any stationary state. Except if you have a magnetic field. If you have a magnetic field, then the guiding equation is also changed a little bit because you have to introduce the vector potential, as you can guess. But for the moment, let's forget about a magnetic field. Things change if you have a superposition, say, of the ground state and first excited state. This is time dependent, it has an interesting phase field, and then things can occur. Actually, the trajectories can get quite difficult. But here the electron just sits there. Now that's maybe not what you would have imagined. On the other hand, who are we to ask what this theory gives us? Maybe that is what happens. Maybe the electron sits there in the ground state. Well, that would at least explain why it doesn't radiate further radiation if it sits there. So, these are just two examples. Of course, you can go on to calculate it for many different examples. What I wanted to discuss now is, if you're already talking about this density and the velocity field, that should remind you of hydrodynamics. In hydrodynamics, I would also talk about the density of the fluid and the velocity field of the fluid and the streamlines of my fluid. And so the question is, can I write down an equation of motion for my velocity field and maybe compare it to hydrodynamical equations of motion? And it turns out, yes, this is possible, and it gives an interesting angle on this whole story. Okay. Now, again, to remind you, V equals h bar over m gradient of the phase, where the phase is taken from the wave function. And now, there are many ways of writing it down, but if psi is the magnitude of psi times e to the I phi, I could say, in order to get at the phase, I take the logarithm of the expression. Now, that of course would also give me the logarithm of the prefactor. But I can then just take the imaginary part of the logarithm. Because that would be the imaginary part of the logarithm of the magnitude of psi plus and what I want to do now is simply, I want to take the time derivative of the phase, so that later, after taking the gradient in addition, I get the time derivative of my velocity field. And then I want to rearrange terms and compare it to hydrodynamical equations. So now, this is probably a calculation which we have to finish next time, but if I take the time derivative of the phase, and I just start from this expression here, I would say, okay, it's the imaginary part of the time derivative of the logarithm. That would be, the derivative of the logarithm is 1 over psi, and then I have to differentiate psi itself. So dt psi over psi. And now at some point, of course, I have to use my Schrödinger equation. So here, the time derivative of psi, I will insert according to the Schrödinger equation. So I will use IH bar dt psi equals minus h bar squared over 2n plus psi plus v times psi. V is the external potential. I'm just looking at a simple particle with mass m. And so here, then, I would have the imaginary part of what? Well, 1 over IH bar, that's the vector stemming from here. And the first term will be taking this Laplacian and dividing it by psi. second term is even more simple. It's just v psi divided by psi, so it's simply v. Okay. Now, let me write it in another way. The second part with the potential is simple. Yeah? 1 over I is minus I, so I get just minus 1 over h bar times v. And this part makes a lot of sense, because if you just remember how a stationary state evolves, the phase goes like minus 1 over h bar times the energy times time. And that's exactly this part. It's the first part that is more interesting. So if I take into account that there is another factor of I here, and I take the imaginary part, I can also express it in terms of the real part, and I will have h bar over 2m real part of Laplace psi divided by psi. So this is what I got so far. Now I want to express Laplace psi in terms of the magnitude of psi and the phase, because in the end I ultimately want to express everything in terms of the phase if possible, or in terms of the magnitude. So what is the Laplace psi? Well, yes. It's the divergence of the gradient of psi, and let me just maybe write down the beginning of the calculation. It's just e to the I phi gradient magnitude of psi plus magnitude of psi I gradient phi e to the I phi. Okay. And then you would once more take the divergence, and you get many different terms and can rearrange them. But the outcome of this then is this real part of Laplace psi over psi can be written in two terms. So there's one term, h bar over 2m, Laplace magnitude of psi divided by magnitude of psi. So that looks very similar, only that now I'm only dealing with the magnitude, no longer with the wave function itself. Minus h bar over 2m gradient phi squared. And then there's this minus 1 over h. So these terms you are not familiar with, but both will have an interesting interpretation. And so let's focus on this grad phi squared term. And let's do a simple calculation on the side. So let's consider what is v grad v. Now this is a little bit funny maybe, but if you ever learned about hydrodynamics, you know that in the hydrodynamic equations of motion, exactly such a term appears. It's sometimes called the advective term, and I will just comment on why it should appear in the end. But let's just calculate it for a moment. So v is h bar over m grad phi. And maybe it's best to work this out in components. So this would be h bar over m squared d I phi, that's from the first velocity, times di, because I'm multiplying with the gradient, and it's a scalar product in here. And then again there's some dj phi from the second velocity. And now you see I can sort of regroup that. This derivative acts on phi, and basically what I have is the dj derivative acting on di phi, di phi. Yeah? This is not quite correct because it can act both on the first and on the second bracket, so it would give twice the result that I desire to have, so that there should be a 1/2. But now you see what is this? That's just grad phi squared. So here I'm taking grad phi squared and then the gradient of that. which is very nice because, of course, all we have calculated so far is only the time derivative of the phase, and in the end we want to take a gradient of that to get the time derivative of the velocity field. Maybe let me just finish these few lines, because now I can collect everything, and I can say, well, the time derivative of my velocity field is h bar over m gradient time derivative of the phase. And now I get several terms. The first one would be minus h bar over m squared 1/2, and that's the term we just calculated, the gradient of gradient phi squared. Then there are other terms. There's, if I collect all the prefactors, minus 1 over m gradient v, the external potential, together with another term, namely this minus h bar squared over 2m Laplace magnitude of psi over magnitude of psi. Okay, so far it's not yet very simple, but we just calculated that this particular term is just minus v grad v. And that term, if you look at it, what we're calculating here is obviously an acceleration. Here's something like acceleration equals 1 over mass times a force. The force is minus grad v, minus gradient of potential, that makes sense. And this part then obviously is also some new addition to the potential, which Bohm termed quantum potential. So if I collect everything and pull this onto the, then I would say this is plus 1 over m times, so to speak, the Bohmian force, where the Bohmian force is minus the gradient of all of this potential. And so if I collect everything, I would say dtv plus v grad v equals 1 over m the Bohmian force field. And the Bohmian force field is just minus gradient v plus the quantum potential. And so that is properly an acceleration. And now just finally, if you don't know hydrodynamics, where does this v grad v come from? It's very easy. If I tell you about the streamlines, and even if the velocity field itself does not change in time, so this first term would be 0, then still a particle flowing along the streamline will automatically change its velocity in time, because it's the streamline, the curves, and so on. So there must be this term to describe the acceleration of the particle. So all of this is really just the acceleration of the particle, and you can convince yourself of that because the first derivative of r, we said, is just v, the velocity field. But it's evaluated at r of t, comma t. Yeah? And so now if I apply the time derivative, there are two parts. There's the time derivative explicitly of the velocity field, but maybe it's stationary. And there is the r dot times grad v part from taking the time derivative of this first term, which just gives rise to the v grad v. So that is standard in hydrodynamics. So you see, this is really the acceleration of such a particle. Okay. So that's the idea. And next time we can discuss a little bit, for example, what does this quantum potential really mean? Yeah? If you look at the ground state of the harmonic oscillator, for example, how does the